Hello. Today we will examine problem 13.21 in fuel efficiency, which connects delta G and delta H. The fuel cell in the problem relies on two half reactions: the reduction of oxygen to hydroxide with voltage 0.4 volts, and the oxidation of hydrogen gas to hydrogen ions with voltage 0. Each of these half reactions involves the movement of two electrons, which we will use later. The first task is to sum up these two half reactions into a single reaction, which just means adding the reactants and products together. The two electrons on each side cancel, and the hydrogen ions combine with the hydroxides to form gaseous water, which also cancels. Lastly, the voltages add to give a total voltage of 0.4 volts. To find the efficiency of the fuel cell, we must next find delta G naught using the equation that relates delta G naught to the voltage. N, the number of electrons, is 2, because each of the earlier half reactions involved 2 electrons. After plugging in Faraday's constant and the voltage and canceling units, delta G naught is negative 77 kilojoules per mole, which indicates the reaction is spontaneous. Now we can find delta H naught by taking the enthalpy of formation of the products and subtracting the enthalpy of formation of the reactants. The relevant information can be found in Appendix E. Here we see the enthalpy of formation of gaseous water is negative 241.8 kilojoules per mole, and because both oxygen and hydrogen gas are in their standard states, the enthalpy of formation of the reactants is just 0. This means delta H naught for the reactions is negative 241.8 kilojoules per mole. Lastly, we can calculate the efficiency by dividing the delta G naught and delta H naught values found earlier. 32% is a reasonable result, since conventional nuclear power stations range from 25 to 30% efficient. So in this problem, we saw how delta G and delta H can be used together to solve real-world problems.